Okay, in this video we are going to do a couple of examples of a smaller topic called algebraic substitution. What happens when a u sub doesn't quite work out perfectly? What happens if I have extra x's? Well, you can sometimes make those work as long as there's only the one extra x. And as long as your relationship, as long as your u term is linear, they're actually going to be fairly easy and fairly okay to work with. Let's go through and let's do them. And we could do an indefinite integral or a definite integral with this algebraic substitution. Either way is fine. But let's try to attack it just like we would a u sub. So you'd look at these two chunks. Remember, there's no product rule, there's no quotient rule, but I'd look at these chunks and I would try to determine which one still has something happening to it. Which one would be more causing the chain rule? And here it would be the 2x minus 1. And then I would take the derivative. I know the derivative of 2x minus 1 would be 2, and then you would kick the dx over. Now, you didn't have a 2 dx. Really, all you had in this question was just the 1x dx. So divide the 2 over. 1/2 of du is going to be equal to dx. Let's switch over what we have so far. The integral symbol is still the integral symbol. And then what's underlined, the dx, you could change that into being your 1/2 du. And then let's look at everything that's left over. Here, let's see, we had the square root of 2x minus 1. Remember, that's u, so that's the square root of u. All this stuff, right? The square root of this stuff, that's the square root of u. And then let's look at the last thing that's left over. I still would need to account for that extra x. And this is kind of a problem, right? The dx switched over. It was the 1/2 in the du. That was wonderful. The integration symbol was the integration symbol. That part gets accounted for. It's the square root of u. But I have this extra x. And how do I potentially get rid of that extra x? Because I don't want this. I don't want to have x's and u's at the same time. That's a problem. It needs to either be all x or all u's. So this seems like it's a problem. But actually, it's going to be pretty okay. All we need to do is go back. Remember, this is your whole key for the question, right? This is how I could switch that chunk. I could switch 2x minus 1. I could switch that into u's. Or if I had just a regular x, right? I switched that whole chunk into u's based on this relationship. If I needed to get rid of a 1x, couldn't I just solve this equation for x? Right? Look at this. You have u equals 2x minus 1. Add the 1 over. That means the x is going to be 1/2 of u plus 1. And now what could I do to get rid of that extra x? Well, I could change it to being in terms of u. I still have the 1/2 out in the front. Of course, I still have the integral symbol, and I still have that du at the end. Like, that stuff is still all there. And then I would still have that square root of u. I'm going to put that as u to the 1/2 power. But now, instead of having that extra x, now I could get rid of that extra x, and I could change it, and I could have 1/2 of u plus 1. Right? So here, that extra x, we could get rid of it by doing an algebraic substitution. You just have to figure out, hey, if 2x minus 1 is equal to u, what would 1x be equal to? If I had that extra oddball x kind of just hanging out, how would I potentially get rid of it? Well, just take that equation, solve it for x, and then plug it in. Now, these questions typically have a little bit of extra work, right? You had the extra algebraic sub to make. And before I integrate, you still have multiplication. So before I integrate, I need to clean this sucker up. Let's see, you got the 1/2 and the 1/2. So that's going to be a 1/4. And then, let's see, the numbers are dealt with. I have a u plus 1 times a u to the 1/2. You're going to have to distribute that stuff. So that's u to the first, u to the 1/2. So that's going to be a u to the 3/2, then plus, and then 1 times u to the 1/2. There we go. You have extra algebra to do for these algebraic substitutions. You have an extra substitution to make, and then before you integrate it, you have some extra simplification to do before you can integrate. But the 2 or 3 extra steps of algebra hopefully shouldn't be the reason why you missed the calculus, right? Because it's really not too bad. You just got to figure out what is the x equal to, plug it in, and then simplify it. and then you could go ahead and integrate it. Don't forget about that 1/4 out in the front. Add 1 to the exponent, divide by that new number. Then the next piece, add 1 to that exponent, divide by that new number. Now this is an indefinite integral, so make sure you put your plus c. Remember the integration symbol and your differential, that drops off. You would either pick up your evaluation bar for a definite integral, or you would put your plus c. And then the last thing is just to kind of reverse substitute. Remember, do not leave it in terms of u's. For an indefinite integral, you must reverse substitute back to x. So I'm going to distribute the 1/4 just to clean it up, and I'm going to reverse substitute, and we're going to get this answer. Let's see. 1/4 times 2/5. That would be 2 over 20. That's going to reduce. You have 1/10. Then you have something to the 5/2 power. Plus, then you have 1/4 times 2/3. That would be a 2 over 12. So that's going to reduce to 1/6 something to the 3/2 power. And then plus c. And then don't forget, reverse substitute back at the end. 2x minus 1 goes in for both of those chunks. And there you have it. This would be the original function, which would give you this as the derivative. It may not look like it right away, but if you were to take the derivative of this and do some algebra, it would simplify, and it would give you x times the square root of 2x minus 1. So that's how you deal with extra x's. You have a little bit of extra substitution, right? Got to get rid of that extra x. You can do it, right? This relationship right here defines the connection between u and x. Just solve it for x and plug it in. So you have the extra substitution, which pretty much always means you have a little bit of extra algebra to simplify before you take the derivative. Before you take the integral. We're undoing a derivative. So we have a couple of extra steps of algebra. That's okay. These ones are still pretty doable. Let's move forward, and then the last two, they got us some definite integrals. How exciting. I'm going to put the squiggles, but remember, you could find the u values if you wanted to. Okay, so here's my u chunk. That's the extra x. So u is going to be 2x minus 1. It's the same thing as the previous question. So then the du would be 2 dx. I don't have the 2. That's okay. 1/2 of du is going to be equal to dx. And now remember, if you take this and if you solved it, I'm not going to redo it all, right? It's literally the same thing that we just did. The x would be equal to 1/2 of u plus 1. So I could get rid of that chunk, right? And I could change that chunk to u's. I could get rid of this extra x. I could change it to 1/2 u plus 1. And then I'm going to put the squiggles. So let's switch all this stuff over. Remember, the x and the dx. Just the dx. That dx is going to switch, and you have a 1/2. And then your du. The extra x right here, the extra x, you're going to change it, and you have a 1/2 u plus 1. Right, so all of this stuff, that's this translation of this extra x. You had the square root on the bottom, so that's going to end up being u to the negative 1/2. And then remember to put your squiggles, or you could switch it over to the u values, or you could put your placeholders. Either way is fine. But I translated it all over. Make sure every single part is accounted for. The dx changed over, brought out this 1/2 also. The extra x switched over. And then that chunk, you have the square root of u on the bottom. Therefore, it's u to the negative 1/2. Now, let's simplify it a little bit. The total coefficient out in the front is going to be a 1/4. And then if you were to distribute, you have u times u to the negative 1/2. So that's going to be u to the positive 1/2 plus 1 times this. So you had the extra substitution to make, which means you have an extra little step of algebra to simplify. And then I can finally do the calculus, which is integrate. So the 1/4 is out in front. Integrate. You have 2/3 u to the 3/2. Plus, when you integrate, that'll be 2 u to the 1/2. You could reverse substitute, or if you wanted to, you could find the u values and plug them in. I'm going to reverse substitute. I'm going to simplify also, distribute the 1/4. So see, that's 2 over 12, so that's going to be a 1/6. Something to the 3/2 power. Reverse substitute. Then I have 1/4 times 2. That's going to be a 1/2. Something to the 1/2 power. reverse substitute. Remember, if this was an indefinite integral, all I would need is a plus c, and then I would be done. We love indefinite integrals. I know it's tempting to forget the plus c sometimes, but indefinite integrals are much less work. Since this was a definite integral, I have to evaluate it. Now, you should not have the squiggles. Once I go back to x, you need to go back to having the x limits. You could have found the u limits and plugged them in for u, but since I like to reverse substitute, I need to go back to having the x limits. Okay, now plug in the 5 for x, plug in the 1 for x. Let's go for it. Here I'm going to have the upper evaluation, which is going to come from plugging in 5, minus the lower evaluation, which is going to come from plugging in 1. Okay, so here we go. 1/6 something to the 3/2 plus 1/2 something to the 1/2. And if I plug in 5, 2 times 5 would be 10. 10 minus 1 would be 9. Did you catch it? So what would the upper squiggle have been? 9. Then let's do the lower so that one would be 9 also. And then let's plug in the 1. 2 times 1 would be 2. 2 minus 1 would be 1. Oh, so the lower squiggle would have also been 1. The squiggles it's possible for them to be the same. Most of the time they'll change. But in this question, the lower squiggle would have been 1, whether you did it with u's or whether you did it with x's. But the upper squiggle, if you wanted to find it, would have been u equals 9. The lower squiggle would have been u equals 1. Again, all you'd have to do is plug in the x value for x and get that corresponding u value. But I like to reverse substitute because for indefinites you would have to. Then you'd put the plus c. But here we go. Let's finish this question. 9 to the 3/2 power. I'm going to do the square root first. So square root of 9 is 3. 3 to the 3rd power is 27. So that's 27 over 6 plus that's 9 over 2. Sorry, that's the square root of 9. That's 3 over 2. 1 to the whatever power. That's just 1. That's just 1. So you can have minus 1/6 minus 1/2. So let's combine some stuff, right? Combine the over 6's. So I've got 26 over 6. And then that's going to be, we have a 3, and then a minus 1, so it's going to be plus 2 over 2. So that's just 1. Or this would be the same thing as 6 over 6. And so here, if you were to combine them, that would reduce also. I think that's 13 over 2, or 13 over 3. If you were to combine them, I think that's 32 over 6, which is going to be divisible by 2. So 16 thirds. Remember, there's other ways, right? There's other ways you could skin this cat, and you could get that final singular answer. You could have combined those two. You could have reduced this, right? And then that would have been 13 over 3 plus 1. That's the same thing as 3/3. That would still get you to the right answer. There's multiple ways you can get to this final singular answer. There's lots of equivalent different answers you could have left it as, but this, I think, is the nicest one. If you put it as a decimal, 5.33333, right, 5.3 repeating, the fraction's much nicer. But we can deal with having the extra x, which is that extra substitution, and that means you have to distribute. You have that extra step of algebra before the calculus. Not terrible, a little bit annoying, but not terrible. Last one, and then we'll be done, which is good, because I'm getting tired. Here we go. What you would do is figure out which chunk to set for the u, x plus 1. So the derivative of x would be 1 plus, so it would be 1 dx. That's lovely. That's going to match. How awesome. Most of the time it's going to kick out a constant. Here it doesn't. So I'm going to have squiggle to squiggle. Now I've got the extra x. You have to figure out what was the extra x going to be equal to. And if u is x plus 1, that means x, subtract the 1 over, is going to be u minus 1. So the dx, you can just straight change it. Dx can straight change it to du. And then I have this extra x on the top. That extra x is going to change, and you'll have u minus 1. Then you have a cube root of u on the bottom, so it'll be u to the negative 1/3. Remember, cube root would be a 1/3. Since it was on the bottom, it needs to be negative. Let us simplify a little bit. Negative 1/3 times 1, so it's going to be a 2/3 power. Right, so you have the extra substitution, right? This chunk right here. the extra x to get rid of, and then you have to simplify, distribute, make that thing a little bit nicer, get rid of the multiplication so that I can integrate, and now we'll actually do the calculus. Add 1 to the exponent, 2/3 plus 1. 1 is the same thing as 3/3, so 2/3 plus 3/3, that's 5/3. And then divide, so it's going to kick out the reciprocal. And let's see, negative 1/3 plus 1 would be a 2/3. And so it's going to kick out a 3/2. And then I like to reverse substitute. So I'm going to have 3/5 something to the 5/3 minus 3/2 something to the 2/3. And then I'm going to go back and switch it to x's, so that something is x plus 1. X plus 1, and if you go back to x's, make sure you go back to having the x limits. You don't have to do it that way, right? You could have just found the u limits and plugged the u limits in for u, but I like to reverse substitute. Okay, plug in the 7. Here we go. We'll have the upper evaluation minus the lower evaluation. It's going to have 3/5 of stuff to the 5/3 minus 3/2 stuff to the 2/3. Let's see, if I plug in 7. 7 plus 1 would be 8. And then let's see, let's do the lower evaluation. If I were to plug in 0, you'd have 3/5, 0 plus 1, so that'd be 1 to the 5/3 minus 3/2. 0 plus 1, 1. Do you see what the upper squiggle would have been? Do you see what the lower squiggle would have been? You're going to do that work one way or the other. It doesn't matter. Do it at the beginning. Then you could just plug in the squiggles, skip the step of reverse substituting. But that requires you to do extra work at the beginning, or you can just reverse substitute and do that work after you do the calculus. Either way, you should get the same thing. All right, here we go. Let's finish this. 3/5, 8 to the 5/3 power. Don't take 8 to the 5th and then try to cube root that really big number. Do the root first, right? 8 to the 1/3 power. The cube root of 8 is 2. 2 to the 5th power is 32. And then here we go. The cube root of 8 would be 2. 2 squared would be 4. You could also do that one. 8 squared is 64. Cube root of 64 is 4. That one's not too bad. 1 to any power is just 1. So that's nice. It's going to be 3/5 times 1 minus negative plus 3/2. Okay, so let's see what all we've got. 3 times 32, that would be 96/5 minus, let's look, 12 divided by 2, that'd be 6. You could leave it as halves. I'll leave it as 12/2. Minus 3/5 plus 3/2. Let's see, let's combine the stuff that's over 5. So that would be 93/5. Then combine the stuff that's over 2, negative 12 plus 3, so that's going to be a minus 9/2. That's a perfectly okay answer, right? If this was a free response, that would be fine. You could have changed this to a 6, and you could have had 6 plus 93/5, and then you would have had plus 3/2. Either way it would work. Or I guess it would be a negative 6. So there's other ways you could write it. If we wanted to get them into a common denominator, I think, or if we wanted to combine them and get a same fraction, we'd have to get a common denominator. That one would have to be made by multiplied by 2. So that would be 186/10. That one you have to multiply by 5, so that'd be 45/10. So if you wanted to get them all together and into one fraction, the common denominator, the least common multiple, right, would be 10. So then, or you could do your fast adding trick, right? That's going to work. And then this answer would end up being 141/10. Okay, which, really quickly, if you wanted to, would be 14.1. That decimal is actually not too bad. But the fraction, I think, is nicer. So algebraic substitutions. What happens when you have an extra x? Well, the world doesn't end, right? Is it a little bit annoying? Yes. Is it very easy to do? Yeah, not very easy, but it's not too bad, right? We've seen much worse this year. So if you have that extra x, you just have to take this equation, right? The thing that ties the x's and the u's together. That defines your whole question. Take that equation, you just solve it for x, then you just plug in and get rid of that extra x, which means you typically always have a little bit of extra algebra. Before you integrate, you have to do that little extra algebra. But there you have it. That's how you do algebraic substitutions.